Хорошо. Okay, so I can begin. Еще, простите, Никита, хочу спросить вас, экран нормального размера?
Да, вроде бы нормального.
Нормально, спасибо. Okay, so I will begin now. Okay, so let's discuss the while character formula. So I recall that G is a complex classical group, so it's GLN or Simplex Group or Orthogonal Group, even or odd. So we choose a maximal torus, which is simply the product of n copies of a punctured complex plane, as before. So I will state the main result, which is a theorem due to Hermann Weyl of, I think, almost a century ago. So the first claim is that the irreducible characters are in one-to-one correspondence with the so-called dominant weights, which form a part, which is denoted by P plus, of a lattice, which is the lattice of the characters of our torus. So these are the dominant weights. I will specify them a little bit later. And now the formula, the second claim, is an explicit formula for the irreducible character, which is indexed by dominant weight. And the formula has the following form. So we have a sum over the elements of a while group. I will specify it a little bit later. Here we have a plus minus, which depends on element of a while group, which is a non-trivial one-dimensional character of this group. And this is my notation for the element of a torus. And this is, we raise it to some power. Here we have lambda, the dominant weight, plus the half sum of positive roots and the action of the element of a while group. And in the denominator, we have just the same expression, only with lambda equal to 0. So if lambda equal to 0, we have equality between the numerator and denominator, and we get 1. So this just corresponds to a trivial character, which is identically equal to 1. And this is a complement to this statement, which says that the denominator function, which is just this one, and initially it is defined as a sum over the elements of a while group, but actually it can be also expressed as a product over the positive roots, and this difference depending on the positive root. So this is an abstract claim which holds for any simple or even reductive Lie algebra or Lie group, complex Lie group. But I would like to specify what happens for our 4 series of classical groups. So this formula can be found in any textbook. But I would like to put an accent to specific formulas for classical groups. But sorry, first I have to discuss first consequence of this beautiful result, which is called the while dimension formula. So the value of a character at the point 1, 1, 1 is just the dimension of the corresponding representation. So this is my notation for the irreducible representation indexed by this dominant weight. And the formula is surprisingly simple. Namely, in our situation, we have a natural scalar product. So I recall that all here happens just in Rn. In Rn, so the lambda and rho and alpha or these objects are vectors in this coordinate space. So we take just the natural scalar product in this Euclidean space. And this is the formula. And again, we see if lambda is equal to 0, we get 1, which corresponds to the trivial representation. So how to prove this formula? The proof is essentially the same as in the particular case of GLN characters, which I already discussed. But let me give a proof because it's quite nice. So what we have? So let's assume that it's convenient to take, I did not write it, take u is e raised to x. So what this means? U is not a single variable but a collection of variables, and this is also a collection of variables. So I assume that x is a vector in, say, complex space. That's not important. But what we have, just substitute as u this object. So we get something like this. I simply rewrite the while formula. And then let x approach 0. So what is the problem? In the initial expression, if you simply substitute 1, 1, 1, we get 0 divided by 0. Okay? You have to resolve this indeterminacy. How to do that? We know a priori that this is a good function. It's just in this variable, it's just a Laurent polynomial. So in fact, there is no problem to specialize it at this point. So this is just the matter of representation. So we understand if you x let go to 0, we get something meaningful. So write this in this way and transform it. Just look what happens. So the first step here is quite trivial. We just transfer this element of while group on the left. This is justified because the while group preserves the action of a while group, preserve the scalar product. So we can put it here, but here we get the W inverse. Next, we use the fact that the W inverse has the same sign as W itself. So one can rewrite the same expression is this way, you see. So we have here the action on the X. But what is important here? Now let's substitute as X rho multiplied by a small parameter. Rho is fixed, epsilon is assumed to be small. Then we get this expression, and epsilon can be put on the left again, no problem. But what we see now, the trick is here. This can be written in this way. So we get here our nice denominator while function. Okay, specialized at this formula. And now we can apply the formula. This is non-trivial fact. I discussed it without great detail before, but we just use this formula. And then, after applying this multiplicative representation, we apply it to it. We get this expression. Okay. But now it's easy. We just look at the first first approximation to this function. It depends on the small parameter epsilon. If you just expand the exponent, the constant term will be cancelled here. And what we get this expression. See? And next we let epsilon go to 0, and we get this expression as we want. So this is essentially the same trick as in the particular case of GLN characters. Okay, now let's discuss case by case what happens for our 4 classical series. First, the easiest case is that of GLN. Now, we don't need even to understand in general what are dominant roots, dominant weights. Just look at the picture, at this concrete picture, what happens for each classical series. So in this case, we already know that the lambdas are the signatures. So these are weakly decreasing collections of integers without any restriction on the sign. The while group is the symmetry group, which permutes the coordinates. The roots are this one. So all this, I recall, happens in the coordinate space, and these are the basis, the standard basis in the coordinate space R. What is rho? Rho is this vector. It is symmetric with respect to reflection. Okay, so this number is minus sine this one. But in this case, it is convenient. It is convenient to get rid of these negative coordinates and just replace it by something which I will denote by delta, just to distinguish it from rho. So we just add this quantity. So at the end, we get 0, and we get this delta. And nothing happens, actually, if you look at the while formula, which is a ratio of 2 expressions. This replacement does not affect the formula. So here we can replace rho by delta. It's a little bit convenient, which is just the question of convenience. And then we get exactly the same expression as we already know well. This is the Schur polynomial, Schur-Laurent polynomial. And the Hermann-Weyl dimension formula for this character turns into this one. I already discussed it before. So this is, we just repeat what we already know for GLN characters. Now discuss the case of a symplectic group.
So in the previous case, we've just we obtained the formula that we started the course with.
Yes.
I mean, so we've deduced it from some general theorems. Is it correct?
Yes, exactly. Exactly. I would like just to demonstrate that this case of GLN is a particular case of a general formula. Nothing new happens here. Okay. Okay, Mish, is it clear?
Yeah,
okay.
That's it.
Okay. So just a moment. What next? What happens for the symplectic group? The main difference here, not the main, but one of the new phenomena here is that the coordinates must be all non-negative. Non-negative, so the condition, we add this condition. The roots, we have more roots. In addition to these roots, we have these roots. I assume I is strictly less than j, And we have a long root, this one. And the while group is also the hyperoctahedral group, the semi-direct product of a permutation group with this group. And this abelian group is formed by inversions. And what is the sign character? It is the usual sign character on the symmetry group. And each inversion has sign -1 in this case. And what is rho? Rho is the same as delta, but plus the ones. So exactly rho has this form. All this is a consequence of a description of a root. We just compute what is the half sum of this, all these objects. So this is easy to see that we get this expression. It's convenient to use this notation for the shifted dominant weight. So this is the L formed in this way. And then we get the following formula. This is just the Hermann-Weyl formula, which can be transformed to this expression. So I would like to emphasize that this is some transformation already of the Weyl formula. It's not in the form which applies to any abstract Lie algebra. This is something specific. And this is just something that I would like to emphasize. So we have this specific form. And I would like to give a proof. How to prove this? You see what happens. You had some alternative sum over the hyperoctahedral group in the general formula, but here we have something different. We have a determinant. How this determinant appears? The argument is as follows. We have the sum of a hyperoctahedral group, which is a semi-direct product of permutations and the abelian part, the inversions. Let's represent a general element of this hyperoctahedral group as a product of two elements. One is permutation, it is here, and then another is responsible for inversions. So we get this expression. And next, it's an easy exercise to see that this interior sum can be transformed to a single product. Because if you open the parentheses here, we get just this sum. Taking into account that the sign of each inversion produces, the sign of each inversion is -1. If you just expand this product, we just get this one. So we have this, and this expression, what we get here is already, it's evident that it can be represented as a determinant, because this is a signed sum, an alternating sum of permutations. So we get this formula in the numerator of a Weyl formula. Okay. Now let's turn to the Weyl denominator, delta, capital delta. What is here? You get this expression. How it is obtained. I recall that the product is over, we use here the multiplicative form for this delta, not the additive, but the multiplicative one. And these three products just correspond to the three parts of the positive roots. This one comes from the long roots. This one comes from these roots. And this one comes from these roots. We see plus and minus just corresponds to plus and minus here. And here we have plus, and this corresponds to this product. So this is in hidden form, this alpha divided by 2, half alpha. This is alpha, so this corresponds to this. And what next? And next we just look at this expression, multiply this and this, okay? And what we get the Vandermonde. This is a simple, very simple. And we have this extra factor, okay? But this extra factor, we divide the numerator, which was here, and this denominator, which is here, we divide by this expression. And what we get just this expression. So this is the result. The result for type C, the symplectic group. What is? I have some problem, I'm sorry. Maybe the screen will disappear. No? Is something happens, I'm sorry. Just a moment, I will try to repair it. What has happened? I'm sorry, I will try to repair. No, I'm sorry, just wait. Sorry, this requires some time. Никита, размер нормальный сейчас?
По-моему, большеват немножко.
Большеват, да? Поменьше сделать, да? Так лучше?
Да, вот так вот хорошо, мне кажется.
Okay. I don't understand what happens, but let's continue. So the case of type B, the odd orthogonal groups. So the description of the dominant weight is exactly the same. Not exactly, actually. It's exactly the same for the orthogonal group, but if you want to be rigorous, we have to include the spinor group, and then we get something more. But in our situation, this does not matter. And I don't want to consider the spinor group. It's not very important, but let's restrict ourselves to to the orthogonal group. So in our situation, this will be the dominant weight, I mean with integral coordinates, because in the case, strictly speaking, for these Lie algebras, for the corresponding Lie algebras, we can also add the possibility to have half integers, which corresponds to this. So, but this is essentially a side remark. This is the description of the root system. It's almost the same as in the case of what happens. Again, I have some problem. I don't understand what happens. Sorry. Excuse me, some problems again. So the only problem, not the problem, but the only difference here is that you have short roots instead of long roots. The while group is exactly the same, but because of this, you have a different row. It differs about 1/2. So we have this picture. But again, this is important. At the end, we have something which is non-zero. Again, we choose this notation L instead of lambda plus rho just for convenience to simplify a little bit the formula. And we get something which looks quite similar to the case of the Simplex group, but only we have 1/2 here instead of simply u and u raised to -1. But there is no problem here, because the L's are also half integers. So actually, this is a correctly defined Laurent polynomial in this variable. There is no problem with actually with this 1/2. We will see this a little bit later in more detail. And again, the van der Monde is in these variables. This is this remark. So this is a Laurent polynomial in the variable. And what is the proof? Exactly the same. No, nothing changes just because the while group does not change. But there is something different in the case of the even orthogonal group, the type D. What happens here? First of all, the description of the dominant weights changes drastically because the last coordinate can be negative in principle. The condition is as follows. This comes because we have a different root system, which looks as follows. And the rho is equal to our delta and takes this form, and L looks as in this way. What is the while group? The while group is again the semi-direct product. Oh, there is again this problem. I don't understand what happens. I'm sorry, I will switch to Russian. Никита, что-то у меня происходит, мой тот самый планшет останавливает вещание. Вы не понимаете, что это может быть? Непонятно.
Он вроде бы не пропадал сначала из зума, и трансляция продолжалась.
Ну,
То есть
не знаю.
мы видели
останавливается.
картинку, и только потом вы сказали, что есть какая-то
Непонятно,
проблема.
что он хочет. Сейчас.
А он что-то сообщает, когда возникает проблема?
Да, он говорит, что нужно перезапустить Zoom. Может быть, это связь какая-то, из-за неустойчивости связи он, может быть, теряет. Ну ладно.
При неустойчивой связи он, по-моему, по-другому говорит.
Сейчас меня слышно?
Да, сейчас слышно.
Может быть, из-за этого. I'm sorry for these problems. So what happens here? Значит, Никита, извините, пожалуйста, еще раз. Значит, если что-то, вы мне тогда давайте знать, если вдруг пропадает у меня связь, пропадет, ладно?
Хорошо, но пока такого ничего не было.
Окей, so... Сейчас, одну секундочку. Я, может быть, у меня там еще как внизу кто-то еще смотрит из-за этого. Just a moment, please, excuse me.
А вот сейчас планшет отключился.
Да. Ну, если это будет продолжаться, я просто возьму маленький перерыв, тогда его переведу в... Сейчас. Давайте попробуем еще раз. Okay, so what I would like to explain. So the while group is a little bit smaller. The abelian part consists only of even numbers of inversions. This means that the restriction of a signed character to this abelian group is trivial. Okay, this is written here. Its restriction to the symmetric group is just the same, but here we have a trivial character on this part. And the obstacle that, because this group is smaller, you can't apply the same trick directly. If you want to replace the summation of the while group by a summation of the permutations, this trick does not work directly. But what we do? To reduce this sum to this one, we need some modification. And the idea is that we have two twin characters which depend on the sign of the last coordinate. Of course, if it's equal to 0, then this sum is just twice the same character. So the idea is to take as the D-type character a reducible character, which is the sum of two twin characters or twice an irreducible character. And due to this little trick, we can repeat our trick and write. Oh, I'm sorry, this is wrong. This is wrong. I'm sorry. This is absolutely wrong. This is D. The D-type character looks as follows. It looks as follows. But again, we have something very similar. Only this concrete expression changes. Okay. And the dimension formula now can be written in some uniform way. We have something which is the same for all these cases, C, B, and D, but some additional factors which appears in type C, in type B, and in type D. So this is just some exercise to transform the abstract Hermann-Weyl dimensional formula to this concrete situation. But now I would like to give the main steps of a derivation of a character formula. So essentially there are, roughly speaking, two methods to prove the character formula. One is some original approach by Weyl himself, and another is some algebraic approach, which does not use integration of the compact Lie group. And here, as we will see, we use the Weyl integration formula. So I recall again the formula, what I would like to prove. And we use some fact from general theory of compact group representations and characters, and specifically the case of classical groups. Okay. So the characters, the first claim that we need is that the characters are Weyl invariant Laurent polynomials, and moreover, the coefficients are integrals, are integers here. So V is my notation for the corresponding irreducible representation. Its character is a Laurent polynomial, which is invariant and with integral coefficients. The first fact. I will explain why it holds. The next claim is that the irreducible characters form a basis. A basis in the space of general Laurent polynomials with arbitrary coefficients, say complex. It's enough. Next, this is some fine algebraic result, but it's not difficult to prove that for each irreducible character, there exists a unique highest weight. So we consider the set of weights of the representations of our representation. I recall this is essentially all monomials. We look at the Laurent monomials, which really appear in the representation of our character. Our character is always some sum of Laurent monomials, and we look at the exponents of its Laurent monomials, and we have a unique highest weight. In this situation, in general, this means that if you add any root to lambda, then we get something which is not in the weight diagram of our representation. So adding a positive root produces something which is not a weight, outside our diagram, our weight diagram. And finally, we have a property which is very important for us. This is just the core of the while method, that the irreducible characters are orthogonal on the compact torus. We take the compact form of our group, and to it corresponds a compact torus, which is just the product of unit circles. And the characters are orthogonal with respect to the radial part of a normalized Haar measure of the compact form. And moreover, as they have a norm 1 with respect to the scalar product. So I will explain. So why this happens, for instance, let me maybe discuss a little bit. The meaning of this property is just, this happens just because we restrict our representation to the compact torus. Okay? And then we look at the characters of the compact torus, and these characters are just Laurent monomials, and each must occur with some multiplicity, which is a positive, non-negative integer. So even we could even put here the coefficients are non-negative integers. So this comes just from looking at the restriction of the representation to the compact torus. This property, this is a consequence of what is called the Peter-Weil theorem. This theorem says that we have sufficiently many representations. So this claim says that we have sufficiently many reducible characters, and this is a corollary of this abstract result, which holds for any compact group, not necessarily Lie group, which is some result for compact topological group. This is another ingredient. The existence of a highest weight is a simple argument, which is actually it is related to what is called highest weight models, Verma models. This is an easy argument. Again, it can be found in any textbook about representations of Lie algebras. This is just because we are looking for finite dimensional representations. This property of finite dimension implies this existence of a highest weight, because otherwise we could get an infinite dimensional module, which is impossible. And this property, the orthogonality property, is a corollary, is a consequence of the sure orthogonality relations for compact group representations. So these are some properties which come from abstract results. So now I come to the structure of the proof. What are the main steps of a proof? So the functions which are produced by the Weil formula, this ratio of 2 sum, indeed satisfy these conditions. We have all these properties. Namely, this is my notation for the function which is produced by the Weil formula. This function is W invariant. This is evident because it is a ratio of 2 skew invariant functions. So the ratio is simply invariant. It is contained here. It has integer coefficients. It's not so trivial, but it can be proved. This requires some work. They form a basis even in the ring with over Z. Not only over C, but over Z. And this is why it happens. We just look at the numerators of the Weyl formulas with sum over W and so on. And we see that they form a Z basis in the ring of skew-symmetric Laurent polynomials. Skew-symmetric just means that they transform according to the sign character of W. In the case of GLN, this is just a skew symmetry. This is easy to see. This is trivial, actually, because we just have, one can say orbit sum. We just anti-symmetrize all monomials. Next, there exists, one can prove, just looking at the formula, one can conclude that there exists a leading monomial. What means leading in this sense? Just in the same sense as we defined highest weight. But here one can say that it is just a leading monomial with respect to lexicographic ordering. This is essentially the same in this case. And the next property is that these functions are orthonormal. Orthonormal with respect to the scalar product which comes from integration on the compact torus with this weight. This is just the factor, the order of the Weyl group. And we take just this denominator, essentially the squared modulus of a denominator. This is also easy because when we integrate, the denominator disappear because they are cancelled with these factors. And what remains are simple expressions. We just have some alternate, how to say it better. Just look, my advice is just look at the case of GLN, which is the simplest case, and then understand that the result is the same for any group, of our type. And finally, we want to prove that any irreducible character is contained in the list of our functions. If you have how to prove this, just take it, and because these functions form a Z basis, we can expand it in this basis, okay? And we get some sum with integral coefficients, actually. And next, we use the fact that the scalar, that the norm of these irreducible characters just equals 1. But all these functions also have norm 1, and they are orthogonal, pairwise orthogonal. This means that in this expansion of these abstract irreducible characters on the basis of our functions, we must have only one summand with coefficient plus minus 1, nothing more. But finally, one can conclude that the coefficient is not minus 1, but plus 1, just by looking at the leading monomial. So this is just roughly speaking, this is the argument. And finally, we have to prove that actually any such function is an irreducible character. But this is because the irreducible characters form a basis Okay, so nothing can be missed here. Otherwise, we could not get a basis in the Hilbert space. So this is just the sketch of the proof. I'm sorry, just a second. So my next goal is to show that these characters, and I recall that this object is a compound character. It's not a true irreducible character, but twice a character or the sum of two twin characters. But this simplifies things. I would like to show that this character CBD, I put aside the GLN case, this is something different here. I would like to show that these are an instance of what can be called multivariable Jacobi polynomials. So my aim now is to explain what this means. So first, a brief reminder about orthogonal polynomials in one variable. So what this means. So probably you know this material, but nevertheless, I would like to recall it. So let M be some measure on the real line with infinite support. So I would like to exclude the case when our measure consists of finitely many atoms. Excluding this, it can be arbitrary, but with the additional property that it has finite moments of all order. This means that integrals of this form with arbitrary n are finite. For instance, we can take any compactly supported measure, and Jacobi polynomials are, in fact, associated with a compactly supported measure, and then this property is satisfied automatically. So the only problem here may appear because if the measure even it can be finite, but it can have the so-called heavy tails. So we want to exclude this possibility. Okay, so now the definition of the orthogonal polynomials associated to this weight measure, or sometimes one call it the orthogonality measure. So these are polynomials P sub n. N is a non-negative integers and infinite sequence. In the case of finite when a measure, our measure consists of finitely many atoms, it's also possible to consider orthogonal polynomials, but in that case, we can produce only finitely many polynomials. But we want to have infinitely many polynomials, so we have, under our condition, we do have infinitely many polynomials, and they are characterized by the property that the degree is exactly equal to n, which means that our polynomials looks like x to n with some non-zero coefficients plus some lower degree terms. So the first property. And the next property is that our polynomial number n is orthogonal to all monomials or to all polynomials of smaller degree. And this scalar product is defined by this integral. I want to consider only real valued functions, so I did not need to put a bar of f2. And these polynomials exist and are unique up to normalization. So it amounts to the choice of the leading coefficients. Up to this freedom, they are unique. And they are obtained by the Gram-Schmidt procedure. We just take the monomial 1, x raised 2, x3, and so on, and orthogonalize them with respect to this scalar product. And then we get our sequence. And now the example that we need, the classical Jacobi polynomials. They depend on two parameters, a and b, which are assumed to be real and greater than -1. The measure is concentrated on the segment from -1 to +1. So this is just the indicator function or characteristic function of. So the measure is contained here. And this weight of this form, this function is integrable because of this restriction. So there is no problem here. And a good reference, just the book, the handbook, Higher Transcendental Functions, Volume 2. It's an excellent source for orthogonal polynomials. No proofs, but very well organized. And so I recommend to look at it. But now something which is not contained in this book, this material, but it is closely related actually to random matrix theory. It becomes now very popular because of this connection. So what are multivariable orthogonal polynomials? So fix our measure, take our orthogonal polynomials, and let's consider arbitrary capital N and arbitrary lambdas, which are the same as in our situation. So these are integral vectors, which are with non-negative coordinates, just as the indices of our characters. And defined a multivariable polynomial indexed by this, one can say, positive signature. By this formula, what we have to notice here, we have this shift. We have to shift here. And this is unavoidable, because in principle, the lambdas, some coordinates can be repeated. And without this shift, we would get 0. But the shifted coordinates are strictly decreasing. So this prevents us from vanishing of this determinant. And we divide it by the Vandermonde. So it's possible, and we get again a polynomial. Why? The same argument as before, because this is skew-symmetric, this is the elementary skew-symmetric expression, and any skew-symmetric polynomial can be divided by the Vandermonde. So what we get is a symmetric polynomial, an ordinary polynomial, not Laurent polynomial, the ordinary. And next we introduced a scalar product for symmetric functions in n variables. By this formula, we integrate them. This is my notation for the for collection of n variables. This is a vector from Rn, and we take our measure, attach it to each variable, but multiply with the squared Vandermonde. And this factor compensates the fact that because we have symmetric functions, we could integrate over the domain but then without factor, without the so this is the same. We can integrate over this fundamental domain with respect to the action of the permutation group, or we can integrate over arbitrary values of the x's, but to compensate this, we introduce this factor. So the result now is as follows. So these are symmetric polynomials. So this is evident. Next, the degree of the polynomial with index lambda is equal to the sum of the coordinates. Why? Look at this. Here the degree is greater with this quantity, but because of the Vandermonde, we actually have exactly the sum of the coordinates. Another argument is as follows. We know that the ratio is some polynomial. Look at its degree and analyze what happens if you multiply it by Vandermonde. What changes? And from this argument, we can see that the real degree is just this one. So this is the idea. And the same idea shows that these polynomials form a basis of a space of symmetric polynomials. Why? This happens because these expressions, I mean the numerators, this determinant or alternants, form a basis in the space of skew-symmetric polynomials. So this just, here we have some transfer from, we pass from symmetric polynomials to skew-symmetric polynomials. Therefore, skew-symmetric polynomials, the claim becomes evident because of the very form of this expression. We could put here any polynomials. It's not important for this claim that these are orthogonal polynomials. What is significant only is that the degree is exactly this one. So they form a basis, and they are orthogonal with respect to this scalar product. I call, what is the scalar product? This scalar product. Why are they orthogonal? Very simple, because when we multiply this scalar product, we have this factor. So this is one polynomial, this is another polynomial. We multiply by this expression. And what we get only the numerators, which we have after this multiplication. So the result is as follows. The fact that our polynomials are orthogonal to this scalar product with respect to this measure is equivalent to the fact that the alternants, I mean the determinants, are orthogonal with respect to this factorized measure without this factor. And the later claim is evident. It's a simple exercise which relies on the fact that we have orthogonal polynomials. So the orthogonality property in one variables is just the source of its claim. The claim about the orthogonality of our multivariable polynomial. So this is the proof. We just have this property. This shows that we have a basis. And this is easy. I just try to explain this. And now let's specialize this general scheme for the particular case of interest for us, for the Jacobi polynomials. So taking the Jacobi polynomials in one variables and using this general device, we get these multivariable polynomials, which are called multivariable Jacobi polynomials. And how is this related to our subject with the characters? So we put aside the GLN case. GLN case corresponds to orthogonality on the torus. There is no symmetry here, which could reduce orthogonality on the circle to orthogonality on the segment, on the interval. So these cases, these two situations, one related to type A and another related to type CBD, they are different. In one variables, they correspond just to orthogonality on the unit circle and orthogonality on the real line. So this is something which make a difference between the GLN and our classical groups. So what is the idea? So the idea that we can regard our character as symmetric functions in, one can say, additive variables or the X variables, where I recall that our U variables, they range in the compact situation, because we need the compact situation because it is related to orthogonality. And in the compact situation, this variable range over the unit circle. Okay? But now we can pass to the additive variables, which are given by this formula, just the real part of this complex number on the unit circle. Why can we do this? But because of the symmetry with respect to the inversion. We got this symmetry using our trick, reducing the Weil group to the permutation group. We had an obstacle, I recall it, in the case of type D, but we can avoid it by by summing two twin representations. So this is just this possibility is just related to the larger group of symmetry, the hyperoctahedral group, instead of a permutation group. So our characters are actually symmetric functions, simply symmetric functions with respect in these variables. So these variables range over this interval. And also I will use the angular coordinates phi, which is just related to U in this way, natural way. And then the X is just the cosine of phi. Okay. Now the result is as follows. As functions of these real variables, x1 and so on, what is here? I'm sorry, this is an error. Sorry. The CBD characters are multivariable Jacobi polynomials. They turn into Jacobi polynomials up to scalar factors, actually. We would like to avoid some little complications related to some normalization. They are Jacobi polynomials with specific values of A and B. 1/2, 1/2, 1/2, minus 1/2, minus and minus. This corresponds to C, B, and D. And again, just note of the fact, if you take the sum of A and A plus B, then we get 1, 0, and minus 1. So the sequence is just corresponds to the C, B, and D. How to prove this? Just look at, just recall what we get. What we get, sorry, I would like just to recall you the formulas. Okay, so this is in type D and something similar, but a different expression here. So remember this. Okay. So what I would like to show that our character, viewed as a function in the axis, looks as follows. So this is some factor which comes from the fact that x is half sum of u plus u to minus 1. So it's not important. And here we have some polynomial of this degree in x sub j. And these polynomials pi are as follows. This one in type C, this one, or this one. So the structure is the same, but some specific choice of this pi. So this is just a consequence of our computation for the while formula. And I claim that these pi's are, in fact, the Jacobi polynomials with the parameters A and B up to scalar factor. But why up to scalar factor? Because I did not specify the normalization of Jacobi polynomials. Okay. Why is it so? But from the very definition of these polynomials, that they are, I would like to say that they are indeed the polynomials. First of all, look at this and just represent them as function of x. Okay, in this case, it's essentially simple. We can divide this by this when we get some symmetric Laurent polynomial, and because it is symmetric with respect to inversion, it is actually a polynomial in x. And the same argument actually holds here, and here it is especially evident. So it's indeed a polynomial in x. It's indeed a polynomial in x, and moreover, we get polynomials which are orthogonal on the real line with respect to the weight measure. Okay, not on the real line first, but they are orthogonal on the unit circle. With respect to the angular, Lebesgue measure on the unit circle, which is the rotational invariant measure. So this is easy because when we multiply by this factor, again, we get rid of the denominator. And what we get with these functions, which are in the numerator are pairwise orthogonal with respect to the Lebesgue measure on the unit circle, but this is evident. So now we want to express this orthogonality property as the orthogonality property on the interval. So we just rewrite this orthogonality measure as some measure on the interval from -1 to 1. And what we get, this is a trivial exercise, we get exactly these Jacobi weight measures. So let me write maybe in more detail what we get. We get this. With specific choice of A and B. This is just a trivial exercise on sine and cosine. So just more precisely, it is convenient to use phi here. So as function of x, it is this elementary expression. And this is well known. This is a particular case of Jacobi polynomial, which is called Chebyshev polynomial of second kind. In this situation, we just have this one, but if we multiply this by u to 1/2 plus to get rid of this 1/2, we get this expression. These are some nameless polynomials, but in fact, they are also a particular case of Jacobi polynomials, but with parameters 1/2 and -1/2. And in type D, we get this expression. This can be written, and this is a polynomial invariable cosine of phi. And this polynomial is called first kind Chebyshev polynomial. These are truly remarkable, very special instance of Jacobi polynomials. So the final result is as follows, that our characters are a particular case of a broader family of orthogonal polynomials. They can be viewed as orthogonal polynomials on the real line. And actually, many properties of characters actually hold in this generality for multivariable Jacobi polynomials. So in particular, one can develop the theory of interpolation polynomials, which I tried to discuss in the very beginning. And we get some theory which works with arbitrary Jacobi polynomials. And again, one can look at the asymptotics of Jacobi polynomials and even more general multivariable orthogonal polynomials as the number of variables n, capital N, goes to infinity. So one gets some theory of, one could say, some analogs in some sense of characters with infinitely many variables in greater generality. So it's, and sometimes even this viewpoint of dealing with orthogonal polynomials has some advantage. But I would like to, finally, I would like to emphasize that the characters are very special instance, and they have some very special properties which are not shared by general Jacobi polynomials. They are very special. It's difficult to explain why is it so, but they have some properties which make them distinguished, easier in some sense. And but there is some double. There are some two viewpoints to deal with characters or to deal with general Jacobi polynomials, which depends on the specific problem. So okay, so I finish now, and you can ask questions, but I would like to